Hi all, this is Mr. Yeager for Honors Chem, and we are beginning our unit on the mole. This is one of those things getting into chemistry. It separates you from physical science. We don't usually do this part in physical science side of chemistry. And it's really where we start using the chemistry and can apply it in ways that normal chemists do in the lab in terms of determining how much of particular chemicals go together. Basically how to start measuring those, okay? The next step with stoichiometry clearly uses this mole idea as well. That's where we can then start predicting how much we should be producing based on how much we put in. So this is just getting the idea of this is how we create solutions, this is how we combine the chemicals, determine what we need to put together, is all through this idea of the mole. All right, so that's what we're basically looking at. All right, we get to finally really use it in our chemical equations, our balanced chemical reactions, after we have figured out the names of those chemical compounds. And I mean, everything kind of is coming together with this, okay? So, the thing is, we're gonna talk about donuts first, okay? With donuts, we usually go to Dunkin' Donuts, Krispy Kreme, you know, one of my favorite places, Da Vinci Donuts, you can order a dozen donuts, all right? And, you know, if I ask you what is a dozen, all right, most of you guys know a dozen means 12. So if I say I have 2 dozen donuts, 2 dozen donuts means I would do 2 dozen, basically times 12 donuts per 1 dozen, right? All right, and I know you're like, oh my gosh, you're doing a conversion. Yes, I am. I mean, whenever you're trying to figure out how many donuts there are in a dozen or how many donuts you're going to get when you have multiple dozens, all you're doing is multiplying that dozen number by 12 and you're figuring out the total number of donuts that you have, okay? And the thing is, does the word dozen specifically have to refer to donuts? The answer to that, again, is no. We don't have to sit there and be like, wait a minute, did you just say a dozen chips? A dozen people? You know, in all those cases, we know you're referring to 12 of something. So that's what we got to kind of keep our mind in. We have other words that we associate with certain values. I mean, I don't know if you've heard of baker's dozen. Baker's dozen means that there are 13, you know, objects. All right. Now, again, we probably wouldn't use that too often outside cooking. But you could sit there and be like, hey, we have a baker's dozen of buses outside, all right? And again, you might be going, why are you saying that? There's 13 buses, all right? But we have other words that are that way. We have like the word couple, okay? Couple means 2 of something. You don't sit there and go, give me a couple of hot dogs. And somebody hands you 7 hot dogs. You'd be like, I said a couple, okay? You know, there are other words out there that, again, represent particular values. I'm going to tell you, I never understand that people think the word few means 3. Okay, I don't understand that at all. But, you know, I have students that always tell me that. I don't sit there and be like, give me 2 fews of these things. People would, again, be looking like I'm an idiot or something. But all I'm really trying to say here is we have certain words that represent certain quantities. Certain quantities, all right? And that is, in the end, what the mole is, okay? The mole is another word that represents a particular number. It's just this number is insanely large, all right? The mole means 6.02 times 10 to the 23rd objects, all right? That is 602 with then 21 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There you go. There is your number. That is the mole, all right? But that's what 1 mole represents, okay? And we'll see why it has to be such a giant number. Clearly, we're not going to use this as something common. We have never said that. You're not going to sit there and go, hey, give me a mole of donuts, okay? In the end, that would probably cover the entire Earth a couple miles deep, all right? You might be like, oh my gosh, there's too many donuts now, but I asked for it, all right? So, you know, that's the idea when we're talking about the mole. It is just another number. So if I say there are 2 moles of something, what would I do? I'd have this number and I'd multiply it by 2. Okay? If I have 3 moles of something, I'd take this number and multiply it by 3. Okay? There shouldn't be any change in how I am doing something just because it's a new word. If I said 2 dozen, nobody would have any questions. If I said 3 dozen, it wouldn't be like, well, this time I'm going to multiply it by 10 and this time I'm going to multiply it by 14. That's just wrong. Okay? So that's what the mole is representing. It is 6.02 times 10 to the 23rd objects. So we have that definition now of what is the mole. All right? So what are we going to do with it? All right? Where is it? How is it really applied? So we have somebody called Avogadro. All right? What we actually had where the mole was developed is from somebody named Amadeo Avogadro. Okay? Yeah, I have this little joke for my students with it. It's like, yep, he looks like the supreme leader, kind of. That's not a great picture of him. All right? The supreme leader, Snoke. Look at him. There it is. That's Amadeo. No, it's not. All right? But what he determined, he was actually a mathematician and physicist, all right, was that at this, what's called the standard temperature and pressure, and we'll see what that is in just a moment, which is shortened to STP, equal volumes of gases had equal number of molecules, regardless of what it was. And I'm sure that was very surprising because, you know, he has carbon dioxide gas, he has oxygen gas, he has nitrogen gas, he has all these different types of gases, all right? If he had them at the standard temperature and pressure, all right, and we'll get into how he developed, like, you know, well, we don't get into it too much, in terms of how he figured out exactly how many molecules there were. It turned out there were the exact same number of molecules of each type, all right? Now, because of their size, there might not be, you know, I don't want to say as many with them, but, you know, they might be different masses involved, and that's what we're going to get into later. But that's where Avogadro came along, and he developed what's called this Avogadro's law. And essentially what that leads to is this Avogadro's number, okay? Avogadro's number is saying, you know, it is a set quantity of molecules, particles, formula units, which he then called the mole, okay? The mole is 6.02 times 10 to the 23rd. That's 6.02 times 10 to the 23rd. We call Avogadro's number, all right? And again, in the end, it can represent anything, but obviously from a chemistry standpoint, it's looking at molecules, it's looking at particles, atoms, or formula units, all right? Just as a quick reset, why do I have all these different things? Remember, molecules are covalent, okay? Formula units is how we count ionic compounds, okay? Compounds, all right? Particles are atoms, that would be the individual atoms themselves, all right? So, 1 mole is equal to Avogadro's number, 6.02 times 10 to the 23rd. That is a constant. That is a constant for 1 mole. Those are 2 completely equivalent values there, okay? All right, so what the heck is standard temperature and pressure, okay? Standard temperature and pressure, or STP, all right, basically means that we have the substance at 273 Kelvin, or 0 degrees Celsius, and standard pressure is 1 atmosphere, or 760 millimeters of mercury, all right? Don't worry about that so much. I only mention it because you'll see problems. They'll say you're at STP, you're at standard temperature and pressure. It doesn't affect how we're going to do the problem right now, at least in this unit. We're not going to really get too much into more of that until we get to gas laws near the end of the year, okay? So how do we end up using the mole, okay? Like I said, it is just like the dozen. Okay, we're not going to do anything separate from the dozen, all right? And I'm going to show this another way too, just so you can see how I like to write it out and encourage my students to write it out, all right? So, how many atoms of carbon do you have if you have 2 moles of carbon? So what do? Well, I start off with 2 moles of carbon, and that's one of those things I will be saying over and over again because, yes, this does involve math, it does involve conversions or dimensional analysis, but it's a very, very consistent process in terms of how you do the problems. You just got to play around with the units, okay? So we start off with the number 2 moles, okay? And we're going to multiply that by 6.02 times 10 to the 23rd atoms, which is divided by 1 mole, because that's based, what we're saying here is this value. If I actually divided this value here, this equals 1. All right, they are equivalent values. All that I'm doing is I'm changing my unit that I'm using. okay? The equivalent amount of atoms is the same whether I say 6.02 times 10 to the 23rd or 1 mole. It's just now I can change my unit involved. So in the end here, and again, it might be easier when I kind of write this out with a couple other problems, all right, is that we just multiplied 2 times 6.02 times 10 to the 23rd. All right, and we get 1.2 times 10 to the 24th atoms. In the second problem, this is basically the opposite. How many moles do you have if you have 5.42 times 10 to the, sorry, just a second, 10 to the 22nd molecules of water? I start out with the number that's given to me, and in this case, I'm going to multiply 1 mole over 6.02 times 10 to the 23rd molecules. All right, and that's again just because I'm trying to make sure I can cancel out the units, and my answer would be 0.0900 moles of water. All right, so that's kind of showing you both ways how we're going to use this, but I'll do a few more examples. One of the biggest things I just want to point out, though, all right, it does not matter at all what the substance is. All right, even though I will be encouraging that you write out what compound, what atom, what object you're using, because that's something we got to be consistent with moving into not only throughout this unit, but next unit and multiple other units, okay? But if I'm going between moles and particles, and when I say particles, molecules, atoms, formula units, it doesn't matter what it is, all right? A mole is the same number of objects regardless of what it is in the end. All right. One other thing to pay attention to, especially my students, is we got to go back and bring back sig figs again. Okay. We got sig figs. The thing with this, though, it should hopefully not be too bad, is that original number is what tells you how many sig figs you need in your final answer. The number that's given to you in the problem. Okay. We never use any of the conversion factors. Otherwise, we'd always be down to 1 digit if we're only dealing with 1 mole. Okay, if we're only dealing with 1 mole. All right, so let me show you a couple examples here. All right, that is not the one I want. We're going to go here. Okay, so let's just do a few because, again, this should get very repetitive. All right, so I'll write it at the top here. We got 1 mole equals 6.02 times 10 to the 23rd, and I'll leave that blank. Particles. I guess I'll just say particles. We'll change it to what we need to say it to. All right. All right. So my first question is, all right, I want to convert all of these moles into particles or whatever they are. In this case, like the first one is just an atom. Okay. So I have 0.25 moles of beryllium. So what I would do there is you write out the number you're starting with. Write it out with the unit, and again, right now, I already encourage you to write the symbol. In the end, the symbol won't do anything, but it's good to know what we're referring to is. Okay. What I would do is, again, I like doing the train track method or whatever you call this with my dimensional analysis. Okay. But the whole idea with this is you can go through it, and you go, okay, I'm in the moles, and I'm trying to go to atoms. What you're coming from goes on the bottom. I'm coming from moles, and I'm changing to atoms, which I'm allowed to do. Moles can change into anything else, and that might be part of where we're going to have some confusion later on, is we're going to change excuse me, moles into grams, we're going to change moles into liters. Later on, we're going to change moles into other types of moles, all right? But moles can be changed into anything else. Any of those other units can never go directly into another unit. Everything has to be connected with the mole, all right? So what I did again is I write out what I start with. What I'm coming from is on the bottom. What I'm going to is on top. When mole is with another unit, mole is always 1. Okay? And that's in our conversion factor here. We're basically just writing in the number from the conversion factor, but this is something that I know helps students. If mole is with another unit in the same block area, like this general, I'll circle it, this general area, okay? Mole always has the 1 in front of it because I do have students that will switch and put the 6.02 at the bottom. Then in front of atoms is 6.02 times 10 to the 23rd. If I multiply that out, which I'm doing right now, this is live. Well, sort of, right? We get 1.505 times 10 to the 23rd atoms. But wait a minute. Okay? That's not the correct number of sig figs. How do I figure out sig figs? I look back at the original number. There's 2 sig figs, so I need to reduce this down to 2 sig figs. 1.5 times 10 to the 23rd atoms. So that's it. Okay? If I do another one, you do the same thing. So I start with 1.33 times, what am I doing? 1.33 moles of bromine. All right, you just leave the bottom blank. Technically, the bottom is like, if you have an empty box, it's just a 1 in there. I go to the next one over. I'm coming from what? Moles, going to, in this case, this would be considered molecules because it is a diatomic molecule. I see moles with a different type of unit, so moles will get 1. Molecules get 6.02 times 10 to the 23rd. Okay? We'll learn really soon that 6.02 times 10 to the 23rd has to only go with atoms, molecules, or formula units. We should never see it run into anything else. All right? So then I multiply these two, 1.33 times 6.02 times 10 to the 23rd, trying to make it exciting. Okay? And I get, let me look at sig figs. I have 3 sig figs at the beginning there, 1.33, all is significant. So this should come out to 8.01 times 10 to the 23rd molecules. And that's what we do with it. Okay? Now, what if I have to go the other way? What if I have particles and I'm trying to get you to go back to moles? All right? The only difference is where the numbers are going to go. The units are going to change, so the numbers have to follow with the units. All right? So if I look at this first one here, I got 3.97 times 10 to the 14th atoms of radium. Since I don't really feel like I have a ton of space, I'm just going to use that right off the bat. All right? You don't have to have the word of, but that's okay. We go to the next part here. I'm in atoms. I'm coming from atoms. What I come from goes on the bottom. What I'm going to goes on top, moles. All right? And this is where I see people make a mistake because they're like, 6.02 times 10 to the 23rd moles. I thought 6.02 goes on top. No. Okay? Moles is with another unit. Moles gets 1. Always, 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 always. What's in front of atoms? 6.02 times 10 to the 23rd. Now, this is where you need to be careful. When you do put in your calculator, like I've talked about before with scientific notation, you need to put this 6.02 times 10 to the 23rd in parentheses when you put it in your calculator, or you need to know how to use that 6.02 e 23rd, that e function. All right, then you don't have to put it in parentheses. So I need to put in parentheses 3.97 times 10 to the 14th divided by 6.02 times 10 to the 23rd. I get a big number, okay? So if I need to go back and look at my sig figs, 3.97. So 3.97 is 3 sig figs, so this is going to come out to 6.59 times 10 to the negative 10th, if you do it with me, moles. Very, very, very tiny. I mean, it definitely will be. You can see I'm way below the 23rd, so it's definitely much, much smaller. Okay? But that's it. That's it, that's it, that's it. The biggest thing here is I'll see people plug this in and they don't plug the 6.02 in the calculator right. They go divided by 6.02 times 10 to the 23rd. The calculator will divide by 6.02 and then multiply everything by the 23rd. And then people get answers of times 10 to like the 46th, the 47th, the, you know, ridiculous answers there. All right? Let's do one more just to see it, and then we're good to go, at least for this first part. So, my second one, 8.4 times 10 to the 29th atoms. This is going to come out to a large number. I'm in atoms. I mean, you can do it this way. What are you trying to go to? That goes on top. What am I coming from? Atoms. The units are different, so mole is always 1. Atoms is 6.02 times 10 to the 23rd. So for this one, 8.4 times 10 to the 29th divided by 6.02 times 10 to the 23rd. I got to convert this some. I'm not going to write that number out. 2 sig figs at the beginning. This is 1.4 times 10 to the 1, 2, 3, 4, 5, 6 moles. And that is it. All right. So hopefully we got through it. We know what the mole is now a little bit. The mole is just a quantity. It's always equal to Avogadro's number, 6.02 times 10 to the 23rd, regardless of what the compound atom formula unit molecule is. Even if we're talking about any other object around us, it's always equal to that quantity, like a dozen, all right? And showed how to kind of go through some of the calculations. Again, use this train track method. What you're coming from goes on the bottom, what you're going to goes on top. Check your sig figs, and you should be all set to go. All right? Have a good one. Oh, need to get rid of that.